Welcome, ladies and gentlemen. Let's take a look at generating a power series representation for a given function. So the key here is being able to rewrite that function so it looks like my basic power series, right? F of x equals 1 over 1 minus x. In this case, it's not going to be 1 over 1 minus x, though it's going to be something like 1 over 1 minus blah, right? So the key is to be figuring out what we're substituting in for that geometric ratio r, or that power series variable x, right, to make this look like our general parent. And so I'm going to go ahead and just do some algebra and rewrite this as 1 over 1 minus something. Can we figure out what that something has to be so that it's equivalent to the original? Well, certainly. It looks like we have to have what? What inside there, Tyler?
Negative 9x squared.
Negative 9x squared. So by rewriting my original as 1 over 1 minus negative 9x squared, we can see exactly what would have to go in my power series representation. Yes? And so it looks to me like if I wanted to rewrite this then as a power series in summation notation, I'll go ahead and start out with my index at 0 to infinity. I know in general that's given by x to the n. When it's my parent power function, when it's my parent power series represented by the function 1 over 1 minus x. But it wasn't x, it was, Tyler told us, negative 9x squared, yes? And so it'll start out of this, and now if you went to check in the back, you probably wouldn't see it written like this, right? You'd probably see it rewritten with the exponent rules applied. So this is your favorite part, right? We'll probably take the negative 1 for alternating sign and put that to the end. We'll probably take the 9 and put that to the n. And we'll probably have x to the, what's x squared to the n? X to the 2n. Good job. Awesome. Go ahead and raise your hand if you had this representation. So did you have the representation as a power series and summation notation? Great. Awesome. Okay, so then how can we check if we're right? Well, we can check and see if we're right by generating the first several partial sums. Kobe?
Is there any reason that we split up the negative 1 and the 9?
I don't think so. I mean, other than that's what I see, that's how I see the answers reported, right? When I look in the back of the book, just like you do, or when I look in the solutions manual, I think that negative 1 to the n is frequently used to generate those alternating signs. When I have those alternating series, like the plus x, minus x squared, plus x cubed, and so on and so forth. And so by putting it out here, it's easy to recognize, and it's easier to add or remove or group if you needed to generate a representation for a series that had alternating signs. More about that later. But I don't know the particular reason other than from familiarity. Emily?
So when you have negative 9x squared to the end, is that just like unfinished, like you can't write that?
That's kind of what Kobe's asking too. Like,
yeah.
Generally you won't see it as this is your final answer. You'll see it more like this, rewritten and regrouped. And I'm not sure the reason for that for sure. Maybe it's easier to see your variable like this, or maybe it's easier to generate the terms. I don't know. I could make an argument for easier to generate the terms like that with the ends too. I don't know. But we're going to have to in either case, right? We're going to have to in just a minute. So what are my first several terms? And we're going to check out on the graph here. Well, it looks like my first several terms then. I'll start with my index value of 0. Plug it in, and I get 0, 0, 0. So it looks like my first term in this series, if I were to expand it, would be 1. And then increment my counter by 1. When n equals 1, I get negative 9x squared. So negative 9x squared would be my second term in the series. And then increment my counter by 1. I'm up to 2 now, right? So I'm up to 2. When n is 2, negative 1 squared is positive. 9 squared is 81. X to the 2 times 2 is 4. Is that correct? And then I increment my counter by 1. I've got 3. And I'm just doing the first 4. Am I doing the first 4? So we're good. I don't have to go to the calculator just to get my constant here, thankfully. So, oh, maybe I will. I spoke too soon. So I'm going to, where am I up to? Am I up to 4 now? No, 0, 1, 2. So I'm up to 3. 3 in for n makes negative 729. Oh, lucky. X to the 6th. And then I know the next one will be plus dot zero. So plus you. We'll show the plus then to represent that this goes on forever and ever. However, we're just going to, for our purposes, graph the fourth partial sum and see how well that does already with only 4 terms. And so let's go ahead and compare these now on the same viewing window. So I probably need this again so that I can enter. And on our graphing calculator, we're going to go ahead and enter our original function before we mess it up. So we'll divide by quantity, 1 plus 9x squared. And then in y sub 2, right, I'm going to go ahead and enter my fourth partial sum would be the sum of the first 4 terms, right, in that series. And so it looks like I want 1 minus 9x squared plus 81. Riley, you got to catch me if I make any. X to the 4th minus 729. X to the 6th. And then this would go on forever and ever and ever, right? But we're just going to graph the fourth partial sum. And so we'll go ahead and grab those first 1, 2, 3, 4 terms and get a suitable viewing window. And so what might be a good window? Oh, we didn't do interval of convergence. We want to do interval of convergence first, and that'll help me determine a good viewing window. So I'm not going to do the window. I'm going to stop right here, and I'm going to go ahead and consider the interval of convergence. How might we generate that, right? Given our original function, well, I know that my original function, right, in a geometric series only converges if my ratio r magnitude is less than 1. So I need x, right? I need the absolute value of x to be less than 1 in my general parent power series function 1 over 1 minus x. But it wasn't 1 over 1 minus x, it was 1 over 1 minus negative 9x squared. So I'll just take that blue, right? I'll take that blue quantity and I'll go ahead and make sure that the magnitude of that blue quantity, negative 9x squared, is less than 1. Then that's guaranteed to converge. So how do we do that? Well, we have to solve this, again, using absolute value. This is negative 9 times x squared, and the absolute value of negative 9 is positive 9. So however you want to rewrite that, right? I'll go ahead and apply the absolute value to that negative 9 and pull it out front. Then I'll divide over to get my absolute value of x squared less than 1/9. Now I can undo those, the squaring in the bars really is my absolute value theorem. I get the positive and negative square root of 1/9 is 1/3. So it looks like our window here of convergence we anticipate to be between negative 1/3 and positive 1/3. If I were to write that as a interval notation, we would go parentheses. And we'll talk more about the endpoints of my interval of convergence right later on in this unit. But for now we'll go like this because that came from a strict. All right, I'm dying to see what this looks like. So that'll help me determine my window. It looks like we're only talking about from negative 1/3 to 1/3. So perhaps I'll only choose negative 0.5 to 0.5. Now that gives me a little clearance on either side, not much. We could certainly do negative 1 to 1 or whatever. I'm going to make my y window, I don't know. My original function though is rational. It was 0, 1, 1, so I want to include 1, so maybe negative 2 to 2. And again, we can just manually adjust that as we see fit. So we'll go ahead and see what that looks like. Here comes my first one. This is the function. The next one will be my partial sums. We only did 4 of them. We want to see how well it does right here in the middle. And it looks like, gosh darn it. Looks like it does a pretty nice job, and that's only with 4 terms. Now, if I wanted to see how nice of a job, it looks like at the center of this power series, the center from where it was constructed at x equals 0, they match exactly. In other words, when x equals 0, the same y value is returned. Well, that makes sense, right? When I plug in 0 to my original function, I get 1, right? And look at that. When x is 0, then all of those x terms will drop out even if I went on forever, and I get exactly 1. Right? You guys see that? Cool. What happens is I scooch over, right, to x equals, what is that, 0.06. We can compare how well they do, 0.9598, 0.599598. Yeah, so it's still pretty good. As I continue scooting over, what happens to the difference in the y-coordinates? It becomes a little bit more pronounced. Now I'm to the thousands. So you see that? Now I'm to the thousands. Hey, that's not too shabby because I'm right? I'm almost halfway in, and I'm only varied by thousandths, and I've only done 4 terms. If I considered the partial sums, if I did the 7th partial sum or the 9th partial sum, you can imagine how accurate this would be. But what happens as I get closer to my end point here of my interval of convergence? In other words, what if I put in something like 0.3? Now you can see visibly, right, the difference there, and I would need more and more, right, higher partial sum values in order to get way back to that close thousandths difference and so on. We're going to talk about error bounds, right, and how many terms we need to include to be within a specified accuracy and precision level as part of our AP curriculum further on in the unit. And so that'll be something, just a little preview that you get to look forward to. Awesome. So who got negative 1/3 to 1/3? You guys get that? Great work, you guys. What questions you guys have about? Oh, I want this too. Oh, no, don't do it. Okay, so that's been not so good, but we're right in time. So let's go ahead and pause the recording and take care of our OTL, please. Okay, ladies and gentlemen. So today we're going to use our discussion last time, right, and how to generate a power series representation for a function and vice versa to generate some new power series as we incorporate the operations we've already worked to develop in calculus both last year in AB and then again this year in BC. Stamped eligible exercises on our activity today include 2B, 4D, 5G, and 6E. And I'll go ahead and include those in our agenda now. And I did scan in, no talking, Q. That's a QG. I did go ahead and scan in my completed activity, and so I'll go ahead and upload that to Moodle as you guys are working, and then you'll be able to check along the way. However, these are the hinge questions that I do want to take a look at when you guys all agree, and we can do this in our cooperative learning groups. And so we're not partner pairs, so you can go ahead and scooch the desks together and get going on that, and then we'll come back together for our closure. I'll go ahead and stop the recording, and you guys can get started. Thank you. Okay, ladies and gentlemen, so let's go ahead and share some of our tools that we have in order to generate new power series representations for new functions. And so I wanted you to do at least 3 different tools and be ready to share, but I can think of 4 or 5, right, just off the top of my head. What are some tools that you guys are developing when you're charged with the task of generating a power series representation for a given function or vice versa? So what's one thing that you guys have been doing? Tyler?
Add a clever 0.
Add a clever 0? That was pretty sweet. Add a clever 0. Hey, that was neat. That allowed us to do what? Well, that made us, gave us a sum in the denominator, right, when we didn't have one. What's another technique that we've been working with? All right, what's another tool in our bag, so to speak? Tyler, thanks for volunteering.
Polynomial long division.
Polynomial long division. Yes. And that was appropriate when what was true? Courtney?
The numerator has either the same or greater x power.
Yes, absolutely. So when the degree of the numerator was greater than or equal to the degree of the denominator, I could use polynomial long division as a means for rewriting that rational expression. Great. Way to go. Dynamic duo, my dynamic duo group. What's another technique that we've used? Or can now use? Oh, come on. Don't be shy. Riley.
Differentiation.
Yeah, we use differentiation, right, to get from a function to a new function using our calculus rules, or even ultimately with the power series representation and summation notation, right? And so differentiation was a means for generating new series representations. Differentiation. Kobe?
That's all I had.
What was the last one? Yeah, integration. Didn't we use integration as a means to successfully generate a new representation for that last one? We were doing that ln, right? So we had to get from there ln. Awesome. Is there anything else we should add? We have Sydney.
We have a question. I don't
Yes.
know if this works. Can you multiply by a clever one? Or
Yes.
Is that not this? Yeah.
Certainly. You can multiply by a clever one.
Okay.
We're trying to think. I know for sure we did that in our context of evaluating limits algebraically without L'Hopital's. We multiplied by that clever one. All right, the 1 over n, the 1 over n. Good. All right, let's go ahead and take a look at the next one. When differentiating or integrating a power series, what happens to the original interval of convergence? All right, and so what happens to the original interval of convergence? We saw that a couple of times at the end there. Danny?
It stays the same.
Yeah, so at this stage we've got our interval of convergence, right, is going to be preserved or remain the same. So the interval of convergence, we're going to say remains the same at this stage. We are going to investigate the endpoints of my interval of convergence later on in the unit, but we're going to go ahead and have the same starting point for now, so it remains the same. Awesome work, you guys. What questions do you have about our discussion and closing today? All right, you're doing a great job. We do have even exercises, page 49, 21 to 31 all, and 35 to 37 all. I'll go ahead and save the recording and then get you those even answers.